Imagine looking up at the night sky and seeing not just points of light, but future homes, colonies on Mars, outposts orbiting distant moons, perhaps even generation ships sailing between the stars. For centuries, humanity has dreamed of reaching beyond Earth, but turning that dream into reality demands more than courage and ambition. It requires technology that can endure silently and reliably for time scales we can barely comprehend. Out there in the void, where radiation shreds electronics, temperatures swing between extremes, and a single mechanical failure can spell disaster, our survival may hinge on a revolutionary idea: motionless machines. These are not the clanking, whirring devices of classic science fiction, but elegant, almost magical systems that harness the fundamental forces of the universe without a single moving part. They draw power from starlight and atomic decay, manage heat through nanostructures, and protect us with fields of pure energy. What makes them extraordinary isn't just their ingenuity, it's their potential to operate for centuries, even millennia, with near-zero maintenance. In this video, we'll explore 30 such marvels, each a testament to human creativity and a key to unlocking the next chapter of our existence. From energy harvesters that turn temperature differences into electricity, to shields that deflect cosmic rays without power, to communication systems that use the galaxy itself as a guide, these technologies don't just solve problems, they redefine what's possible. They promise a future where humanity isn't just visiting space, but thriving in it, sustained by machines so quiet and resilient they blur the line between engineering and art. So come with us on this journey. We're about to unveil the silent guardians that could power human civilization for the next 1,000 years in space and beyond. For decades, our ventures into space have been powered by machines that whir, spin, and pivot complex systems of gears, pistons, and motors that are nothing short of engineering marvels. Yet, these mechanical wonders share a critical vulnerability: movement itself. In the unforgiving environment of space, where temperatures can swing hundreds of degrees in minutes and cosmic radiation bombards everything, moving parts are a liability. They wear down, they require lubrication that can evaporate or freeze, and a single seized bearing or stripped gear can end a mission worth billions. This reliance on mechanical complexity has defined our space age, from the Apollo missions to the rovers on Mars, but it also represents a ceiling we must break through if we are to become a permanent spacefaring civilization. The next 1,000 years of exploration demand a different philosophy, one that embraces the elegant power of stillness. This is where motionless machines enter the story, turning a fundamental engineering constraint into its greatest advantage. Instead of fighting against the harsh realities of space with increasingly complex machinery, these systems work in harmony with them. They leverage passive principles: the constant trickle of heat from a radioactive isotope, the relentless pressure of solar wind, the innate properties of advanced materials that react to light or temperature without a single twitch. This isn't just a minor upgrade, it's a paradigm shift. Think of it as the difference between an intricate, hand-wound watch that needs daily attention and a sundial that tells time for millennia with nothing but sunlight. The recent explosion in nanotechnology, superconductivity, and quantum material science is what makes this shift from theory to reality possible. We can now engineer materials at the atomic level, creating substances that can manage heat, generate electricity, or manipulate light in ways that were once the realm of pure science fiction. This movement toward motionless technology prioritizes longevity and reliability above all else, recognizing that for a mission lasting centuries, the simplest solution is often the most brilliant. It marks a pivotal maturation in our approach to designing for space, where the goal is no longer just to get there, but to stay there forever. Consider the humble thermocouple, a device that generates electricity from heat differences, a principle discovered nearly 200 years ago. Now, imagine that simple idea refined and scaled into a technology so advanced it could power an entire outpost on a distant moon for 1,000 years. This is the promise of thermal energy harvesters, our first motionless machine. In the vacuum of space, temperature isn't just a measure of warmth, it's a powerful, untapped energy currency. These devices master this currency not with turbines or engines, but with solid-state elegance. They function by being placed squarely between two extremes, perhaps the searing heat of a sun-facing side and the profound cold of perpetual shadow. This gradient is the engine, and at the heart of the harvester are advanced thermoelectric materials like bismuth telluride or scuttierudites. These aren't your everyday semiconductors. They are engineered marvels designed with atomic precision to be exceptionally efficient at coaxing electrons to move from the hot side to the cold side, creating a steady, usable electric current. There are no fluids to pump, no pistons to fire, just the silent, relentless flow of energy driven by the universe's own thermodynamics. This makes them incredibly versatile. A probe descending into the frozen depths of a lunar crater, where sunlight never reaches, could draw power from the subtle warmth of the moon's interior versus the surface cold. Conversely, a habitat orbiting close to a star could use the immense heat on its sunward side compared to the frigid void on the other. Their robustness is their superpower. Unlike solar panels, which can be degraded by relentless radiation or coated in abrasive dust, these solid-state blocks have nothing to wear out, nothing to break. They simply sit and work, turning the fundamental contrast between hot and cold into the lifeblood of exploration. A perfect example of working with the environment instead of fighting against it. While thermal energy harvesters turn the environment itself into a power source, our second machine taps into the very fabric of matter, drawing energy from the slow, inevitable whisper of atomic decay. Betavoltaic batteries are, in essence, a form of alchemy, transforming the invisible process of radioactivity into a steady, reliable stream of electricity. The principle is beautifully simple and entirely motionless. Inside these devices, a radioactive isotope, like tritium or nickel-63, steadily emits beta particles, essentially high-energy electrons. These particles are not contained in a violent chain reaction like in a reactor. Instead, they are released gently over many years. Right next to this radioactive source sits a semiconductor junction, similar to what you'd find in a solar panel. But instead of photons from sunlight, it's these beta particles that strike the semiconductor, knocking electrons loose and creating a small but continuous electric current. This process generates only a tiny amount of heat, far less than even a human hand, making it perfectly safe for enclosed environments like a spaceship cabin or a lunar habitat module. There are no moving parts to seize up, no chemical reactions to deplete, and no need for any external fuel source. The energy is simply there, woven into the material itself, waiting to be harvested for decades on end. Think of it as a power source with immense patience. While it only provides a trickle of energy, that trickle is utterly dependable, day after day, year after year, for half a century or more. This makes betavoltaics the perfect sentinel technology. They are ideal for powering the critical systems you cannot afford to have fail. The environmental sensors monitoring air quality on a generation ship, the communication relay storing data until a passing probe can collect it, or the backup computer that must remain in a low-power sleep mode for a century, ready to wake up and execute its programmed task when the time is right. They embody the ultimate set and forget philosophy, a cornerstone for any long-term mission where reliability isn't just a feature, it's the entire point of the endeavor. But energy and power are only part of the equation for long-term survival. The other is protection from the invisible dangers that fill the void. Beyond the comforting blanket of Earth's atmosphere and magnetic field lies a torrent of high-energy particles, a constant sleet of cosmic radiation and sudden, violent outbursts from the sun known as solar flares. For a crew on a multi-generational voyage, this isn't just an engineering challenge, it's an existential threat. Prolonged exposure can damage sensitive electronics, corrupt data, and most critically, significantly increase the risk of cancer and other health issues for anyone on board. Traditional shielding, like thick layers of lead or water, is incredibly heavy and therefore prohibitively expensive to launch. This is where our third machine offers a truly elegant, motionless solution, the static electromagnetic shield. Imagine creating a miniature, portable version of Earth's own magnetic field that envelops an entire spacecraft. That's precisely what this technology does. It uses loops of superconducting wire, cooled to temperatures hundreds of degrees below zero, to generate an immensely powerful and perfectly stationary magnetic field. There are no moving parts, no spinning generators, no adjusting plates. The field simply exists, a persistent, invisible bubble of force. When those dangerous high-energy charged particles approach, this magnetic field acts like an incorporeal shield, gently bending their trajectories away from the ship and its precious inhabitants. It's a defense system that works on the same principle as trying to push the same poles of two magnets together. An invisible force simply won't allow it. The key to its longevity is the superconducting material itself. Once the current is introduced into the supercooled coil, it can circulate with virtually zero electrical resistance, meaning the magnetic field can be maintained for years, even centuries, with almost no additional energy input. It just persists, a silent guardian deflecting harm for generations on end. This isn't science fiction. Prototypes and serious designs for such shields are already being researched by space agencies, representing one of the most promising ways we might finally safely send humans on their longest journeys, wrapped in a protective force field born from the coldest temperatures and the most advanced physics. Now, if electromagnetic shields protect us from the universe's chaos, our fourth machine takes the opposite approach, mastering its most fundamental order, light itself. Photonic crystal reflectors are perhaps one of the most subtly beautiful technologies on our list, working not with brute force, but with the delicate art of precision. To understand their magic, think not of a simple mirror, but of a material engineered at the nanometer scale, with a structure so perfectly ordered it can command light to do its bidding. These crystals are built with alternating layers of different materials, like silicon or titanium dioxide, creating a lattice with gaps precisely tuned to the wavelengths of light we want to control. This structure creates what physicists call a photonic band gap, a range of light that is simply forbidden from passing through, forced instead to reflect with near-perfect efficiency. It's like building a one-way street for photons, dictating their path without a single moving part to direct them. This passive control unlocks incredible possibilities. For power generation, vast, feather-light sails made of this material could be deployed around a space station, focusing and concentrating sunlight from a wide area onto a small, highly efficient solar cell, dramatically boosting energy capture without the mass and complexity of mechanical tracking systems. For communication, these crystals could form the heart of a laser comms array, shaping and directing information-packed beams across millions of miles with minimal signal loss, enabling high-bandwidth conversations with probes at the edge of the solar system. Perhaps most astonishingly, this same principle could be used for a form of passive cloaking. By bending light around an object in a carefully controlled way, a spacecraft could effectively become invisible to certain types of detection, not by active jamming, but by simply wearing a cloak that whispers to light waves, guiding them on a path that conceals what lies beneath. Their resilience is as impressive as their function. In the vacuum of space, there is no oxygen or moisture to cause corrosion, and the same nanostructure that manipulates light is also incredibly resistant to pitting from micrometeoroids or damage from radiation. They don't degrade, they simply persist, silent and unchanging, turning the raw stuff of starlight into a precisely managed tool for power, communication, and stealth. While photonic crystals masterfully direct and shape light, our fifth machine takes a fundamentally different approach. It reimagines the very substance that captures light in the first place. Quantum dot solar cells are not merely an improvement on traditional solar panels. They are a complete reinvention, harnessing the bizarre and powerful rules of the quantum realm to squeeze every last drop of energy from the faintest glimmers of starlight. To grasp why this is such a revolutionary leap, consider the limitation of the silicon solar panels we use today. They are like a net designed to catch only very specific sized fish. If a photon of light has too much or too little energy, it simply slips through without generating any electricity. This is a significant problem as we venture further from the sun, where light is not only dimmer but also skewed toward the red end of the spectrum. Quantum dots shatter this limitation. These are nanocrystals so small that you could fit billions of them on the head of a pin, typically made from elements like cadmium selenide or lead sulfide. Their minuscule size is their superpower. Through an effect called quantum confinement, the size of the dot itself dictates what color of light it absorbs. A larger dot tunes into red light, while a smaller dot is optimized for blue. This means scientists can create a veritable rainbow of quantum dots, each size engineered to harvest a specific slice of the solar spectrum. By layering or mixing these different-sized dots into a single solar cell, they can build a device that captures almost every photon that strikes it, from ultraviolet to far into the infrared. The efficiency gains are staggering, potentially doubling or even tripling the power output compared to conventional cells in the weak sunlight of the outer solar system. But the advantages go far beyond mere efficiency. Because these cells are made from solutions of nanocrystals, they can be printed or sprayed onto almost any surface, like ink onto paper. Imagine the hull of a spacecraft, the flexible wings of a Martian drone, or even the fabric of an astronaut's suit being seamlessly coated with a lightweight, semi-transparent film that passively generates power from ambient light. There are no bulky, rigid panels to deploy and no complex mechanical gimbals needed to track the sun. The power generation is literally baked into the structure itself. This intrinsic flexibility also lends them incredible durability, able to withstand the bending and vibration of launch and the punishing thermal cycles of space without cracking or failing. For a mission to a place like Jupiter's moon Europa, orbiting far from the sun and shrouded in darkness, quantum dot solar cells could be the difference between a probe that operates for a few months and one that gathers data for decades, its power source slowly and steadily drinking in the scarce light, ensuring that our scientific reach extends to the very edges of our celestial neighborhood. Yet for all their brilliance in generating and conserving power, our machines face an insidious and relentless enemy, heat itself. In the airless void of space, there is no atmosphere to carry warmth away through convection, making overheating a silent killer for electronics, life support systems, and human inhabitants. Traditional cooling methods used on Earth with their whirring fans, gurgling liquid loops, and power-hungry compressors are hopelessly inadequate out here. They represent a complex web of failure points, demanding constant energy and maintenance, two resources in desperately short supply on a millennium-long voyage. This thermal dilemma finds its elegant, motionless solution in our sixth machine, the Metamaterial Radiator. This technology performs a kind of magic trick, turning the fundamental challenge of the space environment into its greatest advantage. It cools not by fighting physics, but by embracing it in its purest form. Every object in the universe naturally emits energy as infrared radiation, a process we experience as heat loss. Here on Earth, this effect is often masked by the much stronger processes of conduction and convection, but in the perfect vacuum of space, radiation is the only way to shed heat. Metamaterial radiators are masterfully engineered to be the ultimate emissaries of this radiative process. Their surfaces are not smooth and uniform. Instead, they are nano-patterned with intricate structures that act like a perfectly tuned antenna, but for heat instead of radio waves. This artificial patterning, a feat of advanced electromagnetism and materials science, creates a surface that is almost a perfect blackbody, an ideal emitter of thermal radiation. It can dump heat into the cold depths of space with an efficiency that natural materials could never hope to achieve. The beauty of this system is in its absolute passivity. There are no pumps to circulate coolant, no valves to stick, and no electrical systems to power the cooling process. The radiator simply exists, and by its very nature, it continuously and silently bleeds off excess thermal energy, maintaining the delicate temperature balance required for survival. It's a set-and-forget system in the truest sense, one that could operate flawlessly for centuries without a single moment of human intervention. These radiators could be integrated into the very skin of a spacecraft, or form the backbone of a habitat's thermal regulation system, ensuring that the fragile ecosystem within remains viable not just for a mission duration, but for generations. They represent a quiet triumph of intelligence over complexity, using the cold of the universe itself as an infinite heat sink. While our previous machines have focused on harnessing cosmic energies like light and heat, the void of space holds another, more subtle resource, a constant, gentle rain of dust. Across the solar system, from the rings of Saturn to the empty stretches between planets, countless microscopic particles zip through the darkness. For most of spaceflight history, this dust has been seen as a pure hazard, an abrasive, high-speed sandblaster that can pit windows, degrade sensors, and slowly erode the surfaces of anything it touches. But what if we could turn this pervasive nuisance into a power source? That is the ingenious proposition behind our seventh machine, the Peasoelectric dust harvester. This technology embodies a profound shift in perspective, viewing the space environment not as a series of threats to be mitigated, but as a collection of opportunities to be exploited. At its heart lies a simple yet remarkable principle known as the Peasoelectric effect. Certain crystalline materials, like lead, zirconate, titanate, or even specially engineered ceramics, have a unique atomic structure that generates a tiny electrical voltage when they are physically squeezed or deformed. It's a direct conversion of mechanical stress into electrical energy, with no moving parts required, just the innate property of the material itself. A dust harvester capitalizes on this effect by coating the external surfaces of a spacecraft or habitat with a layer of these piezoelectric crystals. When a micrometeoroid, no larger than a grain of sand, strikes this coating at tremendous speed, its impact creates a minute shockwave, a tiny, localized deformation in the crystal lattice. Instantly, that impact is transformed into a small but measurable pulse of electricity. Individually, each pulse is minuscule, but space is vast and time is long. Over the course of a year, and certainly over a century, a large enough surface area would be struck by millions upon millions of these particles. This creates a continuous, collective trickle of power, harvested from an energy source that was previously only considered destructive. Imagine the hull of a generational ship, its outer skin not just a passive barrier, but an active, power-generating organ. Every tiny impact that would have once contributed to its slow degradation now instead contributes a small charge to its batteries. This energy could be dedicated to powering the vast network of low-power systems that are essential for longevity, environmental sensors that constantly sniff the air for leaks or contaminants, radiation monitors that log exposure over decades, or communication beacons that send out a periodic status ping. It's the ultimate example of a closed-loop system where a problem is recycled into its own solution. This approach doesn't just solve a power need, it fundamentally changes our relationship with the space environment. It demonstrates that survival for 1,000 years isn't about building thicker walls, but about developing a deeper wisdom, a creativity that finds value in the void itself, transforming the faintest whisper of an impact into a building block for the future. If the silent, steady power of a betavoltaic battery is the patient heartbeat of a long-duration mission, and the electromagnetic shield is its unwavering guardian, then our eighth machine is the gentle, persistent hand on the tiller, guiding the ship on its epic journey. For centuries, the very idea of propulsion in space has been synonymous with fire and thunder, the violent, controlled explosion of chemical rockets that hurl spacecraft away from Earth in a spectacular, but tragically short-lived burst of power. That fiery impulse is magnificent for escaping gravity's grip, but it is a terribly inefficient way to travel the unimaginable distances between stars. Chemical rockets are like a sprinter. They expend all their energy in a frantic, powerful dash, leaving them exhausted and adrift. The void between planets, and certainly between stars, is a marathon. And for a marathon, you need an entirely different kind of engine. Enter the static ion thruster, a propulsion system that defies every convention of the rocket age by making silence and slowness its greatest virtues. There is no combustion here, no roaring plume of fire. Instead, the magic happens inside a chamber filled with a noble gas, typically xenon. This gas is first bombarded with electrons to create a soup of positively charged ions and free electrons, a state of matter known as a plasma. Then comes the truly motionless part, a series of carefully shaped electrostatic grids charged with a high voltage, creates a powerful electric field. This field acts like an invisible slingshot, forcefully accelerating the positive ions out of the back of the thruster at speeds that can exceed 110,000 miles per hour. According to Newton's third law, for every action there is an equal and opposite reaction. The spacecraft is pushed forward by the stream of ions shooting backward. The thrust generated is almost absurdly gentle, comparable to the weight of a single sheet of paper resting on your hand. You would never feel this acceleration if you were standing on the ship. But in the frictionless environment of space, where there is no air resistance to slow you down, that tiny, continuous push is all you need. Day after day, month after month, this faint pressure steadily adds up. Over a year, it can increase the spacecraft's speed considerably. Over a decade, it can achieve velocities that chemical rockets could never dream of. This is the essence of the ion thruster's brilliance. It trades raw power for incredible efficiency, using its fuel, the xenon gas, with such frugal precision that it can operate for years on a tank of propellant that a chemical rocket would exhaust in minutes. This makes it the perfect engine for missions measured in human lifetimes. A probe headed to the distant dwarf planets in the Kuiper belt could use an ion thruster for course corrections over decades. A generation ship, a vast ark carrying a civilization to a new star, could use banks of these thrusters for the delicate, constant work of maintaining its position within a fleet, or for making tiny adjustments to its trajectory that compound over centuries into a precise arrival at a new solar system. Their reliability is baked into their simplicity. With no combustion chamber to overheat, no turbopumps to fail, and no moving parts to wear out, the only real limit to their lifespan is the gradual erosion of those electrostatic grids by the very ions they are accelerating, a process that itself is mitigated by advanced material science, allowing these thrusters to operate not just for years but potentially for centuries. They are the epitome of the motionless machine philosophy, proving that the most powerful force in the universe is not a sudden explosion, but unwavering, patient, and silent persistence. While the silent thrust of an ion engine charts our course through the void, and the steadfast hum of a betavoltaic provides power, the most fundamental need for any long-term mission is the very air we breathe. Keeping a crew alive for a year requires a complex, energy-intensive ballet of machines to scrub carbon dioxide and replenish oxygen, typically through a process called electrolysis, using electricity to split water into hydrogen and oxygen. This method, while proven, is a high-maintenance affair. It demands pumps to circulate water, compressors to handle gases, and filters that need regular replacing. It's a system built on movement and constant intervention, a potential single point of failure on a voyage where a spare part might be generations away. This critical challenge finds its most elegant solution in our ninth machine, the passive oxygen generator. This technology does away with the whirring and pumping entirely, instead leveraging the innate chemistry of certain remarkable materials to unlock the oxygen we need, as if by magic. At the heart of these systems are metal oxides such as cerium oxide or various perchlorates. These compounds have a unique and incredibly useful property. When they are heated, they readily release some of the oxygen atoms stored within their crystalline structure. The heat required for this reaction isn't even a burden. It can be scavenged from the waste thermal energy given off by electronics and machinery aboard the ship, or it can be focused directly from sunlight through simple mirrors or lenses. Once the oxygen is released and harvested for the life support system, you're left with a reduced, oxygen-depleted material. But here's the true genius of the closed-loop cycle. If you then expose this depleted material to the carbon dioxide that the crew exhales, a second chemical reaction occurs. The material will greedily absorb the carbon from the CO2, simultaneously releasing the two oxygen atoms back into the air and regenerating itself back to its original metal oxide state, ready to be heated again to start the process all over. It's a beautiful, self-sustaining dance of chemistry that requires no moving parts, just the careful application and removal of heat. There are no seals to fail, no pistons to wear out, and no delicate membranes to clog. The entire apparatus could be little more than a series of stacked ceramic honeycomb blocks housed within a simple, insulated chamber. One side of the chamber is heated by waste energy, releasing oxygen for breathing. The carbon dioxide-rich air from the habitat is then routed over the depleted blocks, which scrub it clean and release more oxygen, all without a single pump or compressor. This passive reliability transforms life support from a high-anxiety engineering challenge into a silent, background process. For a colony on Mars or a generation ship bound for the stars, it means the air itself becomes a renewable resource, managed not by complex machinery, but by the timeless principles of chemistry and heat. It ensures that the most vital element for survival flows ceaselessly, a quiet testament to the power of working with nature's own rules rather than forcing our way through with mechanical complexity. Yet even as we master the chemistry of air, we confront another elemental force that defines the cosmos, the pervasive, bone-chilling cold. In the sun-drenched regions of space, thermal management is about shedding excess heat, but venture into the shadows, the permanently dark craters of the lunar poles, the frigid surfaces of distant moons like Europa, or the profound emptiness between stars, and the challenge flips entirely. Here, the enemy is not heat, but the utter lack of it, a cold so absolute it can freeze fuels into useless sludge, shatter metal with its contractions, and silence electronics in a permanent, deep frost sleep. Active heating systems with their electrical resistors and complex thermostats are a poor solution for the long haul. They drain precious power and introduce a web of failure points. This is where our 10th machine reveals its profound, silent utility, the radioisotope heater unit. This technology represents perhaps the most pure and direct application of atomic physics for human survival. At its core is a small, rugged pellet of a radioactive isotope, most famously plutonium-238. This material is not undergoing a chain reaction. There is no explosion, no meltdown risk. Instead, its atoms are simply, slowly, and inevitably decaying, a process that releases energy consistently in the form of heat. It's a built-in property of the element itself, a tiny piece of the universe that is forever warm. This decay heat is then harnessed in the most straightforward way imaginable. The radioactive pellet is sealed inside a multiple-layer, crash-proof capsule designed to survive any conceivable accident, and this entire unit is then mounted directly to the component that must be kept warm, perhaps a sensitive computer, a thruster fuel line, or a critical sensor. There are no wires to carry electricity, no heating coils to burn out, no switches to flick. The warmth is generated right at the source and conducted passively into the surrounding hardware, creating a stable, life-giving thermal bubble in the infinite freezer of space. The longevity of these units is what makes them legendary. A single pellet of plutonium-238 has a half-life of about 88 years, meaning it will still be producing a significant amount of its original heat a century from now. This isn't a battery that depletes, it's a clock that ticks down so slowly its warmth feels eternal on human timescales. We have already seen their irreplaceable value on missions like the Voyager probes, which, decades after leaving Earth, still rely on their gentle heat to keep instruments functioning in the interstellar dark, and the Curiosity rover on Mars, which uses them to survive the frigid Martian nights. For a future outpost inside a shadowed lunar crater, where water ice reserves are mined in perpetual darkness, banks of these passive heaters could be embedded into the habitat's foundations, ensuring the walls never frost over and the plumbing never freezes solid. They are the ultimate off-grid survival tool, a testament to the idea that sometimes the most reliable warmth doesn't come from a roaring fire, but from the patient, unfailing glow of a tiny sun contained within a rock. If the radioisotope heater unit is a silent sentinel against the cold, then our 11th machine is a patient gatherer, turning the very dust of other worlds into the building blocks of empire. For centuries, mining has been a brutal, mechanical affair, a symphony of grinding gears, pounding pistons, and roaring engines that tear into the earth. This approach is unthinkable in space, where gravity is weak or absent, where every vibration risks shaking delicate instruments loose, and where abrasive dust, known as regolith, can spell doom for any machinery with moving parts. The challenge of harvesting resources from the surface of an asteroid, the Moon, or Mars demands a completely different philosophy, one of gentle persuasion rather than violent extraction. This is the realm of the electrostatic particulate collector, a device that uses the subtle, invisible force of static electricity to do the work of a bulldozer without ever making a sound. The principle is one you've likely experienced yourself on a dry winter day: the faint crackle and pull when a balloon rubbed against your hair suddenly attracts tiny pieces of paper. The collector amplifies this simple effect into a powerful, precise tool. Imagine a series of flat panels or a slowly rolling drum, perhaps deployed from a rover or a stationary lander. These surfaces are charged to a high electrical potential, creating a powerful electrostatic field around them. As the fine, dry dust of an alien world is kicked up by a gentle puff of gas, or even just settles naturally in the low gravity, these charged particles are irresistibly drawn toward the collector, sticking to its surface like iron filings to a magnet. The process is utterly silent and requires minimal energy, just enough to maintain the electrical charge. There are no grinding drills to blunt, no screeching conveyor belts to snap, and no complex gears to jam with grit. Once a layer of precious material has been collected, the system simply reverses the charge, causing the particles to release and fall into a waiting container, ready for processing. The potential of this technology to enable what scientists call in situ resource utilization, literally using the stuff you find there, is nothing short of revolutionary. A probe landing on a water-rich asteroid could use these collectors to gently gather frost-covered regolith without ever disturbing the volatile ice, which would simply sublimate away if exposed to the heat of a traditional drill. On the Moon, they could be used to harvest the soil not just for scientific study, but for its practical wealth, extracting oxygen locked in minerals for breathing air, or silicon and metals for 3D printing construction materials right on the spot. This transforms the entire economic model of space exploration. Instead of launching every single nut, bolt, and bottle of water from Earth at astronomical cost, we can learn to live off the land, using these silent, efficient gatherers to slowly, steadily stockpile the resources needed to build, to fuel, and to sustain ourselves. It shifts our role from desperate visitors carrying all our supplies in a suitcase to savvy settlers who know how to use the materials at hand, ensuring that our expansion across the solar system is not just possible, but sustainable for the long millennia to come. While traditional solar panels are effective, they often demand significant surface area and precise orientation to maximize their energy capture, constraints that become critical when every square inch and ounce of mass counts on a space mission. This challenge finds an ingenious and almost artistic solution in our 12th machine, the luminescent solar concentrator. Imagine if the very windows of a Martian habitat or the transparent dome of an orbital station could do more than just offer a view. Imagine if they could also silently, efficiently power the world within. That is the elegant promise of this technology. At its heart lies a beautifully simple principle inspired by nature itself. Think of the way a jellyfish or a firefly naturally produces light through bioluminescence. The luminescent solar concentrator works in reverse, performing a kind of alchemy on sunlight. It starts with a transparent panel, much like a pane of glass or a sheet of plastic. Embedded within this clear material are special molecules, highly efficient fluorescent dyes, or, in more advanced versions, tiny semiconductor crystals known as quantum dots. When sunlight strikes this panel, these embedded particles spring into action. They absorb the broad spectrum of incoming photons and then, in a process called fluorescence, re-emit that energy as light at a very specific, lower wavelength. Here's the crucial part. Due to the optical properties of the transparent material, this re-emitted light becomes trapped inside the panel itself, bouncing along its length like a signal traveling through a fiber optic cable. The panel is essentially guiding and concentrating this captured light, funneling it toward its edges. Waiting there, lining the thin borders of the panel, are small, highly efficient strips of conventional photovoltaic cells. These cells are now presented with an intensely concentrated beam of light, far stronger than the diffuse sunlight that originally struck the entire large surface area. This allows them to generate significantly more electricity than they ever could on their own, all while being tucked away out of sight. The advantages of this motionless approach are profound. First, it eliminates the need for bulky, heavy, and power-hungry mechanical systems that constantly tilt and rotate traditional solar arrays to track the sun. The entire broad surface of the concentrator is its collector. It doesn't need to move because its internal chemistry does all the work of gathering and directing energy. This also means these concentrators can take on shapes and forms that are simply impossible for rigid panels. They can be curved, molded, or even made flexible, allowing them to be seamlessly integrated into the very architecture of a spacecraft or habitat. A station could have observation decks where the panoramic windows are also major power generators. A rover could have a transparent, shell-like canopy that powers its instruments while protecting them. The mass savings are equally significant as you replace heavy support structures and motors with lightweight, multifunctional sheets of material. Furthermore, their passive nature makes them exceptionally durable. With no external moving parts to be damaged by micrometeoroids or degraded by radiation, and with the photovoltaic cells safely shielded and only experiencing a concentrated but steady flow of light rather than the harsh thermal cycles of direct exposure, the entire system is poised for incredible longevity. This makes them perfectly suited for deployments where maintenance is a fantasy, such as a remote outpost on Pluto or a probe sent on a millennia-long journey into the Oort cloud. They represent a paradigm shift in how we think about power generation, moving away from dedicated mechanical hardware and toward a future where the environment itself, the very structures we live and work within, becomes a silent, persistent partner in our survival, quietly turning the faintest starlight into the energy that sustains our journey. Yet, even as we master the art of gathering power and resources with silent grace, some of the most critical systems for a long-term mission still require one fundamental thing: rotation. The spinning of a gyroscope for navigation, the whirl of a turbine in a cooling loop, or the rapid rotation of a flywheel storing vast amounts of kinetic energy, all are essential for maintaining stability, managing thermal loads, and providing backup power. For centuries, this spinning has come with an inevitable, grinding cost: friction. Wherever two surfaces touch and move against each other, even with the most advanced lubrication, there is wear. Over a decade, this wear is manageable. Over a century, it becomes a guaranteed point of failure. Over a millennium, it is an existential threat. This is the ancient problem that our 13th machine solves with a touch of literal magic: the passive magnetic bearing. This technology doesn't just reduce friction, it banishes the very concept from the equation. It accomplishes this by leveraging one of the most fundamental and powerful forces in the universe: magnetism. The principle is one of perfect, stable opposition. By using powerful permanent magnets, or in more advanced systems, superconductors cooled to extreme temperatures, these bearings create powerful magnetic fields that repel each other with incredible force. A rotating component, like the shaft of a flywheel, is suspended within a housing not by physical ball bearings, but by this invisible, ceaseless push. It floats perfectly centered in a cushion of magnetic force with a hair's breadth of empty space separating it from any solid surface. It is levitation, pure and simple. The implications for longevity are staggering. A flywheel used for energy storage, spinning at tens of thousands of revolutions per minute in such a bearing, would experience zero mechanical wear. There is no contact and therefore no degradation. The only forces acting against its spin are the faint whispers of atmospheric drag, which is irrelevant in the vacuum of space, and the minuscule effects of residual magnetism. This allows such a system to maintain its spin, and thus its stored energy for years, potentially even centuries, with near-perfect efficiency. The silence is equally profound. The characteristic whine of high-speed machinery is born from the vibration of physical contact. Remove that contact, and the operation becomes utterly noiseless. This is not just a matter of comfort for a crew, but of precision for sensitive scientific instruments that must be isolated from any vibrational interference. For a generation's ship on a centuries-long voyage, such bearings would be the silent, beating heart of the vessel's most critical infrastructure. The massive flywheels storing energy for night cycles, the turbines circulating atmosphere and water, the navigational gyros keeping the ship on course, all could operate continuously, maintenance-free, for the entire duration of the journey. They represent the ultimate fusion of motion and stillness, proving that even when movement is essential, it can be achieved with the eternal, unwavering patience of a motionless machine. But even with the silent hum of magnetic bearings and the steady trickle of power from quantum dots, a human outpost in space requires something even more fundamental: water. It is the lifeblood of any colony, essential not just for drinking, but for growing food, producing oxygen, and even creating rocket fuel by splitting it into hydrogen and oxygen. Launching enough water from Earth to sustain a community for centuries is a logistical and financial impossibility. The answer, then, must be found in situ, drawn from the very environment we seek to inhabit. This brings us to our 14th machine, a technology that seems to perform a kind of alchemy, conjuring liquid treasure from seemingly barren ground: the static water extractor. Unlike the industrial pumps and drills we might instinctively picture, these devices operate on a principle of gentle, passive persuasion, harnessing the subtle forces of physics to do the hard work without any power or moving parts. The magic lies in the materials themselves. Imagine a specially designed membrane or a block of porous material engineered to be intensely hydrophilic, a term that literally means water-loving. This material possesses a powerful capillary action, the same natural phenomenon that draws water up through the roots and stems of plants against the pull of gravity. On a world like Mars, where water exists as ice or as tiny traces of humidity in the atmosphere, these extractors would be deployed directly into the regolith or exposed to the air. The hydrophilic material acts like a microscopic sponge with an irresistible pull, actively attracting and wicking any available water molecules toward itself. Once captured, the system can then utilize the planet's own natural temperature swings. As the sun heats the extractor during the day, the trapped water is released as vapor. It then travels through the system, perhaps condensing on a cooler, shaded surface, where it drips down as pure, liquid water into a collection reservoir. The entire process is a closed loop of capture and release, powered entirely by the diurnal cycle of the planet itself, requiring no external energy input whatsoever. The most advanced designs for these extractors don't just rely on simple chemistry. They look to biology for inspiration in a field known as biomimicry. Scientists have studied the ingenious way the Namib desert beetle survives in one of the driest places on Earth. This remarkable insect has a bumpy shell with hydrophilic patches that attract microscopic water droplets from the morning fog, which then channel down into its mouth. Similarly, the structure of a cactus spine is perfectly evolved to condense and direct precious moisture. By reverse engineering these billion-year-old natural designs, we can create artificial surfaces that are exponentially more efficient at harvesting water from even the most arid environments. For a settlement on the red planet or a research station on a distant moon, the implications are profound. Vast arrays of these passive extractors could be laid out across the landscape, silently and continuously pulling water from the thin air or the icy soil day after day, year after year, filling underground storage tanks that serve as the colony's aquifer. This technology transforms a hostile world into a provider, turning a critical survival challenge into a managed resource. It ensures that a community's water supply is not dependent on a complex, power-hungry filtration plant that could break down, but on a distributed network of silent, steadfast, and maintenance-free machines, guaranteeing that the most vital resource for life flows freely for generations to come. Perhaps the most profound challenge of deep space isn't the cold or the radiation, but the soul-crushing, absolute silence of isolation. The knowledge that a message sent from a probe orbiting a distant star would take years, decades, or even centuries to reach Earth, making real-time conversation or command an utter impossibility. This light-speed barrier isn't just a technical inconvenience, it's a fundamental wall imposed by the laws of physics as we currently understand them. A wall that seems to forever condemn interstellar explorers to a state of irrevocable solitude. It is against this daunting backdrop that our 15th machine emerges, not as a finished technology, but as a breathtaking theoretical concept that dares to ask, what if we could cheat the universe's ultimate speed limit? The Quantum Entanglement Communicator is a device that exists at the very frontier of theoretical physics, a proposal so revolutionary it feels like it was pulled from the pages of the most ambitious science fiction. Its promise hinges on one of the most bizarre and counterintuitive phenomena ever discovered: quantum entanglement. This is the eerie property where two particles, often photons or electrons, can be linked or entangled in such a way that their properties become inextricably intertwined, no matter how far apart they are separated across the cosmos. If you were to measure the state of one particle, say, its spin or polarization, the state of its entangled partner would be instantly determined, seemingly communicating that information faster than the speed of light. This spooky action at a distance, as Einstein famously called it, appears to offer a loophole, a potential backdoor for instantaneous communication. The vision for a communicator based on this principle is the ultimate motionless machine. Imagine two boxes, one left on Earth and the other carried on a ship headed for Proxima Centauri. Inside each box is a collection of thousands, perhaps millions, of these delicately prepared entangled pairs. The device itself would have no traditional moving parts, no transmitters, no dishes to aim, no complex mechanics. It would be a solid-state apparatus designed to carefully measure its set of particles in a precise sequence, with the act of measurement on one end theoretically causing a correlated, instantaneous change in the particles light years away. Decoding that sequence of changes on the receiving end could, in theory, reconstruct a message, a string of ones and zeros, that arrived not years later, but in the very same instant it was sent. The implications are almost incomprehensible. A colony on a world 10 light-years away could have a live video conference with mission control on Earth. A probe discovering an alien ocean on a distant moon could send its data to home the moment it was collected, allowing scientists to analyze it in real time. It would utterly shatter the feeling of isolation, weaving a web of instant connection across the vast, empty stretches of the galaxy, and making the concept of a disconnected, lonely outpost a thing of the past. Yet, for all its majestic promise, this technology remains firmly in the realm of theory, and for a critically important reason. While the correlation between entangled particles is indeed instantaneous, the process of actually using that correlation to send a meaningful message faces a monumental and possibly insurmountable hurdle known as the no communication theorem. In essence, the person measuring the particles on the receiving end has no control over what result they get. The outcome of each measurement is completely random. They see only a random sequence of ups and downs, spins or polarizations that looks like meaningless noise, without a separate, classical light speed message from the sender explaining how they measured their own particles to create that specific pattern of randomness. The received data is useless. It's like having one half of a pair of magic dice that always match. If you roll a 6 on Earth, your partner on Mars instantly rolls a 6 too. But you have no way to force your die to land on a 6 to send a predetermined signal. The roll is always random. You'd still need to send a slow radio message saying, "I just rolled a 6 at exactly 10 o'clock, for them to know what their own die showed and to understand it as a piece of data. This is the central paradox that physicists are desperately working to overcome. Current research is exploring incredibly complex and subtle ideas, like quantum teleportation protocols and the manipulation of entire clusters of entangled particles in ways that might just sneak a bit of information through this loophole. The very act of pursuing this dream, however, is driving monumental innovation in the field of quantum computing and precision measurement technologies that themselves are rich with potential for other motionless systems. So, while a practical quantum communicator may be a vision for the far future, its value today is immense. It serves as a North Star for engineers and physicists, a guiding concept that pushes the entire field toward deeper thinking and more elegant solutions. It embodies the highest aspiration of motionless technology, to solve the most intractable problems not with force and complexity, but with a profound understanding of the universe's most subtle and powerful rules. It is a testament to the human spirit's refusal to accept limits, a promise that even the void between stars may one day be bridged not by a roar, but by a whisper, a silent, instantaneous connection across the unimaginable emptiness. While we dream of technologies that weave instant connections across light years, we must also confront the silent, invisible threat that permeates every corner of space: radiation. This isn't the kind of radiation you might think of from a science fiction movie. It's a constant, insidious drizzle of high-energy atomic particles streaming from the sun and deep space, capable of passing straight through a spacecraft's hull and, more worryingly, through the bodies of anyone inside. For a mission lasting years, let alone centuries, understanding and monitoring this exposure isn't just a scientific exercise. It's a matter of life and death, essential for predicting cancer risks, managing crew rotations to shielded areas, and planning the long-term health of a spacefaring population. This critical task of vigilance falls to our 16th machine, a device of beautiful, almost archaic simplicity in a world of quantum complexity, the passive radiation decimeter. Unlike active sensors that require power to run and complex electronics to interpret their readings, these decimeters are the silent historians of the cosmic environment. They work not by doing anything but by simply being. At their core are special materials with a remarkable property. They absorb energy from radiation and store it, trapped within their atomic structure, like a tiny battery being charged by invisible rays. Two of the most common are thermoluminescent crystals, often made of lithium fluoride, and radiochromic films, which are essentially sophisticated, self-developing photographic film. When a high-energy particle zips through one of these materials, it bumps electrons within the crystal or polymer lattice into a higher energy state, where they become stuck. There they remain, a perfect, unalterable record of the event, accumulating over seconds, days, and years. To read the data, you don't plug the device into a computer. For the crystals, you gently heat them in a special reader back in the lab. The trapped electrons release their stored energy as a faint pulse of light, and the intensity of that glow directly corresponds to the total radiation dose absorbed. The film, meanwhile, undergoes a permanent color change, darkening in precise proportion to the exposure it has received. The sheer elegance of this system is in its utter passivity and resilience. A crew member on a generation ship would wear a small badge containing one of these materials, much like hospital workers do today, quietly building a personal log of their exposure. Meanwhile, arrays of them would be mounted strategically throughout the vessel on the bridge, in the agricultural modules, deep within the most heavily shielded living quarters, creating a detailed, three-dimensional map of the radiation environment over the entire structure. Their data would be invaluable not just for the current crew, but for their children and grandchildren, providing a centuries-long environmental record that could reveal long-term trends in solar activity or the passage through regions of space with unusually high radiation. This information would directly shape the most intimate decisions of the mission: how long a person can safely work in certain areas, when to retreat to storm shelters during a solar flare event, and even informing reproductive health and genetic planning for the future of the colony. In a vessel filled with the hum of ion thrusters and the glow of quantum dot arrays, these small, silent badges and plates are the unsung guardians of biological destiny. They require no software updates, no calibration, and no power. They simply endure, bearing witness to the invisible ocean of energy we sail through, ensuring that the story they tell isn't just one of exploration, but of survival itself. In the intricate web of systems that keep a space habitat alive, constant vigilance is paramount. The air must be breathable, the pressure stable, and the structural integrity unwavering. A single, undetected micrometeoroid puncture or a slowly leaking valve could spell disaster, especially when a rescue mission might be years or even generations away. Relying on complex electronic sensors with their delicate circuitry and constant power, demands for this eternal watch is a precarious gamble. This is where the 17th machine introduces a paradigm of silent, material-based sentience, the electroactive polymer sensor. Imagine a material that can feel its environment and communicate what it feels, not with a digital readout or a blaring alarm, but through a physical, visible change in its very form. That is the core magic of these devices. They are crafted from special smart polymers, long chains of molecules engineered to be exquisitely sensitive to specific stimuli in their surroundings. Some are tuned to react to minute changes in pressure, while others are designed to swell or contract in the presence of certain chemical compounds or to shift shape with the slightest variation in temperature. The response is direct, immediate, and requires no intermediary computer or power source. The environmental change itself provides the energy needed for the material to deform. This principle of direct transduction, turning one form of energy into another, is what makes them so brilliantly passive and reliable. The applications within a long-duration mission are as diverse as they are critical. Picture the outer hull of a generation ship, its inner surface coated with a thin, nearly invisible layer of a pressure-sensitive polymer. If a tiny piece of space debris were to strike and create even a pinhole leak, the local drop in air pressure would cause that specific patch of polymer to wrinkle or change its optical properties, creating a visible mark that pinpointed the breach's exact location for repair crews. Inside airlock doors or around critical plumbing, strips of chemical-sensitive polymer could be adhered to joints and seals. Should a dangerous toxin like ammonia from a cooling system begin to leak, the polymer would undergo a dramatic color change, perhaps shifting from clear to a vibrant, unmistakable red, instantly alerting anyone nearby to the hazard without a single watt of electricity or a line of code being executed. Even within the suits astronauts wear outside, these materials could be woven into the fabric itself. A suit glove made with a temperature-responsive polymer could change color if the exterior temperature climbs to a dangerous level, giving the wearer an immediate, intuitive warning directly on their fingertips. The beauty of this technology lies in its distributed intelligence. Instead of having a few expensive, complex electronic sensor suites that could fail, you can blanket an entire habitat with these cheap, durable, and disposable polymer patches. They create a continuous, analog safety net that is always on, always watching, and utterly immune to power outages, software glitches, or electromagnetic pulses. They represent a shift from centralized digital monitoring to a more organic, holistic form of environmental awareness, where the very walls themselves can sense and signal danger, ensuring that the first line of defense isn't a circuit board, but a cleverly designed material that speaks the silent language of physical change. Yet, even as we build walls that can sense leaks and materials that can warn us of danger, a spacefaring civilization must confront a far more fundamental and constant biological reality: waste. On a mission lasting centuries, there is no way to throw things to. Every piece of organic refuse, from food scraps to human sewage, represents not just a disposal problem, but a catastrophic loss of precious, irreplaceable atoms, the carbon, hydrogen, oxygen, and nitrogen that are the fundamental building blocks of life itself. To see this waste as anything other than a resource is a luxury our planet affords us, but one that vanishes the moment we leave its cradle. This is where the 18th machine performs its quiet, vital alchemy, transforming what we discard into the very substances that will sustain us, the static waste converter. Forget the image of a complex processing plant with grinding macerators, roaring incinerators, and pumps shuttling liquids everywhere. This technology is the antithesis of that industrial clamor. Instead, it employs the oldest recyclers in the universe, bacteria and catalysts, and gives them a permanent, optimized home to do their work in perfect silence. Imagine a series of stacked, honeycombed panels or long, gently winding tubes, all with interiors coated in a microscopic forest of nanotechnology. This nanoscale texture vastly increases the surface area available, creating a metropolis for specialized microbial communities or impregnated with powerful catalytic agents. As liquid and solid waste slowly flows through this labyrinth, drawn by gravity or gentle capillary action rather than mechanical pumps, it comes into contact with these biological or chemical workhorses. For wet waste, anaerobic bacteria, organisms that thrive in environments without oxygen, would break down the complex organic molecules, a process that naturally produces two incredibly useful byproducts: methane, which can be captured and used as a clean burning fuel for cooking or supplemental power, and a nutrient-rich slurry that serves as a potent fertilizer. For solid compost, a different suite of aerobic microbes would work in tandem with fungal networks to decompose the material into a rich, earthy humus, perfect for enriching the soil of agricultural modules. The entire system is a lesson in passive, elegant design. The heat required to maintain the ideal temperature for these microbial cultures can be scavenged from the waste thermal energy of the habitat's other systems. The flow of material can be managed through clever, gravity-fed architecture or the use of hydrophilic materials that wick liquids along without a single moving part. There are no blades to dull, no filters to clog and replace, no motors to burn out. It is a garden of decomposition working tirelessly in the background, invisible and inaudible. On a Mars colony, this technology transforms the entire concept of sanitation from a cost center into a production line. The colony's restrooms aren't the end point of a waste stream. They are the beginning of a resource harvesting operation. What goes in one end is, over time, converted into the fuel that helps power the habitat and the fertilizer that nourishes the crops that will become the next meal, literally closing the loop on the carbon and nitrogen cycles. This isn't just efficient engineering, it is the literal embodiment of a circular economy, a system that mirrors the most resilient ecosystems on Earth. It ensures that a distant outpost can become truly self-sustaining, not by launching endless resupply missions, but by mastering the ancient, silent art of renewal, turning what was once considered refuse into the very foundation of continued life. But even as we master the art of turning waste into wealth, the very mind of the spacecraft, its central computer, faces a challenge of time and endurance. The silicon chips we rely on today are marvels of complexity, but they are not built for the ages. They generate heat, are susceptible to cosmic rays flipping bits of memory, and their intricate, nanoscale pathways can slowly degrade over decades of constant use. For a mission whose timeline is measured in centuries, a traditional computer represents a fragile brain in a resilient body. This vulnerability leads us to our 19th machine, a concept that reimagines the nature of computation itself, not with electrons shuttling through silicon, but with pulses of light dancing through crystal, the Photonic Turing machine. This isn't merely a faster computer, it's a different kind of thinking entity, one whose very operation is as timeless and motionless as a beam of light. The theoretical foundation rests on the work of Alan Turing, who conceived of a simple machine that could solve any computable problem by reading and writing symbols on a tape. A photonic version of this replaces the physical tape and its moving head with pathways of light. Imagine a perfectly clear, solid crystal, its interior etched with incredibly fine channels and resonators, a labyrinth for photons. Into this maze, you inject pulses of laser light, each pulse representing a single bit of information, a 1 or a 0. The magic happens as these light pulses travel through the crystal's engineered circuit. By manipulating the properties of the light itself, its phase, polarization, and intensity, and how these pulses interfere with each other, the system can perform logical operations. It can add, subtract, compare, and store information, all through the passive guidance of light through its static, unmoving architecture. There are no electrons to collide and generate waste heat, no transistors to switch on and off and eventually wear out. The computation is achieved through pure optics, a silent ballet of light whose only movement is at the speed of light itself. The potential benefits for a millennia-long voyage are staggering. The processing speed would be orders of magnitude faster than anything possible with electronics, enabling a starship's AI to make complex navigational calculations in real time as it traverses uncharted space. More importantly, its durability would be nearly absolute. Without moving parts or sensitive electronic components, it would be largely immune to the effects of radiation and temperature fluctuations that plague conventional computers. Its energy consumption would be minuscule, as the primary energy required is for the initial light source. and the computation itself happens with incredible efficiency as the light pulses interact. This means the ship's brain could remain awake, alert, and intelligently guiding the mission for century after century, without degradation or the need for Chinese letter cycles that could cause it to miss a critical event. It could continuously monitor every other system on the vessel, from the integrity of the magnetic shield to the nutrient levels in the hydroponic farms, making autonomous decisions to optimize and repair based on a deep, long-term understanding of the ship's health that no human crew could ever maintain. While this technology remains largely in the theoretical and experimental realm, with laboratories around the world working to create stable, complex photonic circuits, it represents the ultimate convergence of the motionless machine philosophy. It proposes a form of intelligence that is as permanent and reliable as the crystal it is etched into, a silent, enduring mind capable of shepherding humanity through the long, dark night between stars, ensuring that the mission's purpose is never forgotten and its path is never lost. While the notion of floating effortlessly through a spacecraft might seem like the ultimate fantasy of space travel, our bodies are hardwired for a world with constant, relentless gravity. Remove that fundamental force for months or years, and the human form begins to unravel in silent, devastating ways. Without the daily resistance of gravity, bones no longer feel the need to maintain their density, leaching calcium and becoming frail. The heart, a muscle that constantly works against gravity to pump blood upward, weakens and becomes less efficient. Muscles atrophy from disuse, and the body's entire fluid distribution system is thrown into chaos, often leading to vision problems and a host of other medical issues. For a mission lasting a few months, astronauts can combat these effects with rigorous daily exercise regimens, but for a voyage spanning generations. You cannot expect an entire civilization, from infants to the elderly, to spend half their lives on a treadmill. This biological imperative leads us to our 20th machine, a system that doesn't just support life but fundamentally recreates the conditions for it, the passive gravity simulator. This technology offers the most elegant solution to one of the most non-negotiable requirements for long-term health in space, the constant, reassuring pull of weight. The most straightforward and brilliantly passive method is centrifugal force, the same phenomenon you feel on a spinning carnival ride that seems to push you outward. Imagine a space station or a generational ship designed not as a series of boxes, but as a vast, rotating wheel or cylinder. As this entire structure spins steadily around its central axis, anything and anyone inside it would be pressed outward against the inner rim of the hull. To the people living there, this force would feel indistinguishable from gravity. Their feet would stay firmly on the ground. They could walk normally, and fluids in their bodies would behave as they do on Earth. The entire habitat becomes its own gravity machine, and the only moving part is the entire structure's rotation, maintained by gentle, occasional thrusts from motionless ion engines or reaction wheels. There are no vibrating platforms, no complex pistons simulating weight, just the silent, constant spin of a world they can call home. For designs where a large rotating section is impractical, an even more motionless approach exists using the principles of diamagnetism. Certain materials, and indeed all living tissue to a very small degree, are repelled by magnetic fields. While too weak to be felt on Earth, this force could be harnessed in the zero-G of space. By creating powerful, static magnetic fields oriented in a specific direction, say, from the floor to the ceiling of a chamber, scientists could create a uniform force that gently pushes against astronauts, effectively pinning them to the deck. It would be like lying on a bed of magnetic repulsion, a constant, invisible pressure that mimics gravity's pull. the energy required is only to maintain the magnetic field, which, if generated by superconducting coils, could be nearly negligible. This system has zero macroscopic moving parts. The gravity is generated by a perfectly stationary field, offering a truly silent and maintenance-free solution. The impact of such technology on a multi-generational voyage cannot be overstated. It transforms the ship from a fragile, zero-G hospital into a robust, familiar environment. Children would develop with strong skeletons and healthy cardiovascular systems. Everyday activities like eating, drinking, and sleeping would happen naturally, without the complications of floating liquids or the need to be strapped into a sleeping bag. Even the simple psychological comfort of feeling grounded, of having a clear sense of up and down, would be a monumental boost to morale and mental health over decades. It represents the ultimate application of clever physics to solve a biological problem, ensuring that the human body remains as resilient as the ship that carries it, generation after generation. While the gentle spin of a gravity simulator ensures our bodies remain strong and our minds feel grounded, the very air we breathe within that environment demands an even more constant and vigilant form of care. Every exhale from every crew member releases a silent, steady stream of carbon dioxide, a gas that is harmless in tiny amounts but becomes a toxic, suffocating blanket if allowed to accumulate. On a mission lasting generations, managing this invisible exhaust is not a matter of periodic filter changes. It is a continuous, non-negotiable process of renewal, a literal recycling of life itself. Traditional active systems with their whirring fans, power-hungry compressors, and complex networks of sensors and valves represent a terrifyingly long list of potential failure points for a community that cannot step outside for a breath of fresh air. This is where the 21st machine introduces a profoundly elegant and steadfast solution, the static atmosphere scrubber. This technology performs the critical work of air revitalization, not with mechanical complexity, but with the silent, hungry intelligence of advanced materials. At its heart are substances known as chemical absorbents, with two families standing out as particularly remarkable. The first are zeolites, naturally occurring or synthetically produced minerals with a microscopic honeycomb structure that acts like a sponge for specific molecules. Their pores are perfectly sized and charged to attract and trap carbon dioxide, pulling it directly from the air that passes over them. The second, even more advanced group are metal organic frameworks, or MOFs. These are crystalline materials that can be custom designed atom by atom in a lab, creating nanostructures with such immense surface area that a single gram can have an area larger than a football field. This vast internal landscape is covered in molecular docking stations that are exquisitely tuned to latch onto CO2 molecules with incredible efficiency, scrubbing the air to a purity that active systems struggle to match. The true genius of these scrubbers, however, lies not just in their capture ability, but in their capacity for rebirth. Once the material becomes saturated with carbon dioxide, it doesn't need to be thrown away, it can be regenerated. This is where the system achieves true passivity. The entire scrubber unit, perhaps a series of stacked cartridges lining the walls of a habitat's air circulation plenum, can be gently heated using the waste thermal energy from the ship's electronics, or by simply redirecting a trickle of sunlight through a fiber optic line. As the temperature rises, the chemical bonds holding the CO2 weaken, and the trapped gas is released in a concentrated stream, ready to be either vented into space or, more cleverly, captured and used as a raw material for producing methane fuel or even nutrients for hydroponic farms. Once purged, the absorbent material cools down and is instantly ready to begin its work again, its appetite for toxins completely restored. This creates a perfect closed-loop cycle of capture and release, a silent, endless dance powered by the waste products of the very life it sustains. There are no motors to burn out, no filters to clog, and no delicate sensors to miscalibrate. The system's reliability is baked into the immutable laws of chemistry and the enduring stability of its solid-state construction. For a generation ships sailing for centuries, these silent, wall-mounted guardians would be among the most critical pieces of technology on board, working tirelessly in the background to ensure that every breath taken by every descendant of the original crew is as fresh and life-giving as the first. They transform the immense challenge of maintaining a planetary atmosphere inside a metal hull from a high-stakes engineering problem into a managed, passive process, proving that the key to long-term survival often lies not in adding more moving parts, but in understanding the deep, silent language of molecules. As we consider the silent, steadfast systems that manage our atmosphere and simulate the gentle tug of gravity, another profound challenge of the space environment presents itself: the sheer difficulty of handling and storing the physical objects of daily life. In the weightlessness of orbit or on the surface of a low-gravity moon, nothing stays put. Tools drift away, supplies must be meticulously tethered, and the constant battle against floating clutter becomes a surprising drain on time and focus. More critically, the movement of heavy equipment or sensitive instruments using traditional methods, cranes, conveyor belts, or even robotic arms, introduces friction, vibration, and mechanical complexity, all enemies of longevity. This logistical puzzle finds its most elegant and almost magical solution in our 22nd machine, a technology that seems to defy the very nature of reality: the quantum locking device. This innovation doesn't just move things, it elevates them quite literally into a state of perfect, effortless suspension. The principle at work is one of the most visually stunning demonstrations of quantum physics, a phenomenon known as flux pinning. It begins with a special material called a high-temperature superconductor, typically a brittle, ceramic-like compound. When this material is cooled below its critical temperature using something as simple as liquid nitrogen, it undergoes a dramatic transformation, becoming a perfect diamagnet. This means it actively repels magnetic fields. Now, introduce a powerful permanent magnet, like one made of neodymium. Instead of just pushing the magnet away, something extraordinary happens. As the magnetic field lines try to penetrate the superconductor, they become trapped within tiny imperfections in its crystalline structure. These trapped field lines act like invisible pins, locking the superconductor in place relative to the magnet at a fixed distance. The result is not just levitation, but incredibly stable suspension. You can tilt the entire apparatus, and the superconductor will not slide off or drift away. It will stubbornly maintain its position, hovering in mid-air as if glued there by an unseen force. It's a demonstration that feels less like engineering and more like wizardry. Now, translate this from a laboratory curiosity to the practical environment of a space station. Imagine a storage bay where sensitive scientific instruments, containers of delicate genetic samples for agricultural research, or even heavy spare parts for machinery are not stored on shelves or in locked cabinets, but simply float in designated positions within a framework of permanent magnets. There is no physical contact, and therefore no risk of scratches, abrasion, or the transfer of vibrational energy that could disrupt delicate calibrations. The act of retrieving an item becomes as simple as gently plucking it from its invisible magnetic cradle. Replacing it is just a matter of letting go, allowing the quantum lock to seamlessly re-engage and hold it perfectly still. The energy requirements for this system are almost non-existent after the initial cooling. Maintaining the superconductor at its required temperature in the cold vacuum of space is far less energy-intensive than it is on Earth, and the magnetic fields are provided by permanent magnets, which demand no power at all. This represents the ultimate in frictionless, maintenance-free operation. The potential extends far beyond static storage. Picture a network of these magnetic tracks running through the corridors of a large space station or a lunar base. Carts carrying supplies could glide along these pathways without wheels, gears, or motors, propelled by gentle pushes or pulled by targeted magnetic pulses, all without a single part ever touching or wearing down. This would revolutionize logistics, turning the movement of mass from a power-hungry, noisy, and mechanically complex operation into a silent, graceful, and virtually eternal ballet of levitating objects. It exemplifies the highest ideal of the motionless machine philosophy, proving that the most counterintuitive and delicate phenomena of the quantum world can be harnessed to solve the most mundane yet critical problems of daily life, ensuring that the effort of building a civilization among the stars is met not with resistance, but with effortless, magical ease. Yet even with the effortless grace of quantum locking and the silent renewal of air and water, a spacecraft adrift in the incomprehensible vastness between stars faces a navigational dilemma of epic proportions. How do you know where you are when every familiar landmark is a distant, unmoving pinprick of light, and the very concept of a roadmap stretches across light years? For centuries, ocean navigators on Earth looked to the stars for guidance, and in a beautiful twist of cosmic irony, the solution for navigating the sea of space returns to that ancient wisdom, but with a precision those early sailors could never have dreamed of. This brings us to the 23rd machine, a system that uses the universe itself as its only instrument, the passive navigation beacon. Forget the idea of a physical machine with blinking lights or transmitting antennas. This technology is the ultimate expression of using what is already there. It taps into the most reliable and consistent timekeepers in the cosmos pulsars. These are the ultra-dense, rapidly spinning corpses of massive stars that went supernova. As they spin, they emit powerful beams of radiation from their magnetic poles, much like a cosmic lighthouse. If Earth is in the path of that beam, we observe it as a perfectly regular pulse of energy, flashing with a rhythm so precise it rivals our most advanced atomic clocks. Each pulsar has its own unique signature, a specific rate of spin that identifies it like a celestial fingerprint. The concept for deep space navigation is then one of breathtaking elegance. A spacecraft would be equipped with a simple, robust sensor, essentially a small X-ray or radio telescope designed to listen to the heavens. It scans the sky, listening for the rhythmic ticks of these distant lighthouses. By detecting the signals from 3 or 4 known pulsars and measuring the exact timing of their pulses, the onboard computer can perform a feat of triangulation on a galactic scale. It compares the arrival time of each pulse against a pre-loaded database, a map of the expected pulse timings as they would be observed from a known point, like our solar system. The minute differences in when these pulses arrive tell the spacecraft exactly how much farther it is from each pulsar, allowing it to calculate its position in 3-dimensional space with astonishing accuracy, potentially down to a few kilometers, even when light years from home. The beauty of this system is its profound passivity and independence. It requires no energy-intensive transmissions from Earth, which would take years to arrive and could be disrupted. It has no moving parts to wear out. The sensor is just a static receiver listening to the eternal ticking of the universe. Its reliability is guaranteed for millennia because it is built upon the immutable physics of neutron star rotation, a clockwork that will continue long after our sun has grown cold. This autonomy is the key to true interstellar exploration. A generation ship bound for another star cannot rely on instructions from a mission control that will be generations dead by the time the message is received. It must be able to navigate for itself, to correct its course based on its own observations of the cosmos. This pulsar-based system provides that capability, offering a constant, unchanging reference frame that is available anywhere in the galaxy. It represents the ultimate fusion of fundamental astronomy and practical engineering, a technology that humbly accepts the guidance of the universe itself, ensuring that no matter how far we wander, we are never truly lost, but simply learning to read a map written in the timeless pulses of dying stars. While the steady ticking of pulsar beacons charts a course through the galaxy, the vessel itself needs a way to travel that immense distance, a form of propulsion that matches the timescale of the journey. For centuries, the dream of sailing to the stars has been hampered by the tyranny of the rocket equation, which demands impossible amounts of fuel for any meaningful interstellar speed. But what if the fuel tank could be left behind, and the ship could instead ride upon a wind that has been blowing since the birth of the sun? This is the revolutionary promise of the solar sail, but our 24th machine takes this concept a crucial step further into the realm of perfect stillness, the electrostatic solar sail. Imagine a spacecraft that moves not by expelling its own mass, but by simply holding up a giant, invisible hand to catch the constant stream of particles rushing outward from the sun. This solar wind is a plasma, a thin gas of charged particles, mostly protons and electrons flowing past at speeds of over 1,000,000 miles per hour. A traditional solar sail, much like an oceanic sail, relies on physical momentum transfer. Photons of sunlight, though they have no mass, carry a tiny amount of momentum, and when they reflect off a giant, ultra-thin mirrored sheet, they push it forward. It's a brilliant, passive concept, but it has a key vulnerability: the enormous, fragile membrane itself. Deploying a sail that can be kilometers across requires a complex and risky mechanical ballet of booms, spars, and motors. A nightmare of potential failure points for a mission lasting centuries. The electrostatic sail elegantly sidesteps this entire mechanical dilemma. Instead of a solid sheet, it consists of multiple long, thin conducting wires, perhaps only a fraction of a millimeter thick but stretching for dozens of kilometers. These wires are charged to a high positive voltage by an electron gun, a simple device that shoots out negative charges to leave the wires positively charged. This creates a powerful positive electric field around each wire, an invisible force bubble extending dozens of meters into space. As the positively charged protons from the solar wind approach this extended electric field, they are strongly repelled. It is this repulsive force acting across a vast invisible area that slowly but surely pushes the entire spacecraft forward. There are no gigantic sheets to unfurl and tear, no complex rigging to manage. The sail is not a physical object at all, but a structured electric field, deployed simply by unreeling a few strong, lightweight wires and turning on a power source. The steering mechanism is equally motionless and brilliant. By individually adjusting the voltage on different wires within the array, the craft can change the shape and orientation of its invisible magnetic sail, allowing it to tack against the solar wind much like a clipper ship tacks against the oceanic wind, altering its course without a single mechanical actuator. This ability for electronic, software-based control eliminates the need for any moving parts to adjust the sail's attitude. The acceleration provided is incredibly gentle, far less than the weight of a coin resting in your hand. But here, in the frictionless environment of space, patience is the ultimate fuel. Day after day, year after year, that minuscule push continuously adds up. Over a decade, a probe could reach speeds that would take a chemical rocket immense fuel loads to achieve. Over a century, it could be cruising at a significant fraction of the speed of light, all without ever carrying a single drop of combustible propellant. Its fuel tank is the sun itself, and its engine is nothing more than a cleverly arranged electric charge. This makes it the perfect propulsion system for an interstellar arc or a long-range survey probe destined for the Oort cloud. It embodies the core philosophy of the motionless machine, achieving the grandest of ambitions not through explosive power and complex machinery, but through unwavering, silent, and intelligent persistence, harnessing the eternal currents of the cosmos for a journey that may well outlast the civilization that launched it. Now consider the silent, ceaseless battle every machine in space must wage against temperature, a war fought not against the bitter cold of shadow, but against the relentless, building heat generated by its own operation. Electronics, life support systems, even the metabolic warmth of a living crew, all produce energy that must be continuously bled away into the void to prevent a catastrophic meltdown. Traditional thermal management relies on active systems, pumps that circulate coolant, louvers that open and close, and fans that whir to life, a symphony of moving parts that introduce complexity, consume power, and represent a long catalogue of potential failures over a 1,000-year mission. This dependency on mechanical intervention finds its most elegant and steadfast solution in our 25th machine, a technology that embeds intelligence directly into the very materials that surround us, the passive thermal switch. This isn't a switch you flip. It's a switch that flips itself, responding to the environment with the silent, innate wisdom of a material changing its very state. At its heart lies the simple, profound physics of phase change materials. These are substances, like certain salts or specialized waxes, that absorb or release large amounts of energy when they transition between solid and liquid states. This transition point, their melting or freezing temperature, is their set point, their entire reason for being. Imagine a critical computer processor on a deep space probe. It's mounted onto a heat spreader that isn't just a simple piece of metal, but a matrix impregnated with a phase change material, engineered to melt at exactly the processor's maximum safe operating temperature, say 80 degrees Celsius. Under normal operation, the material remains solid, but if the processor begins to overwork itself, perhaps during a complex calculation, its temperature starts to climb. As it approaches that critical 80-degree mark, the magic begins. The phase change material doesn't just get hotter, it begins its transformation from solid to liquid, a process that consumes a massive amount of thermal energy, the latent heat of fusion. It acts as a microscopic, self-deploying heat sponge, soaking up the dangerous excess energy and holding the processor's temperature steady at that safe maximum, preventing any further rise. Once the computational load lightens and the heat output drops, the material begins to cool, slowly releasing that stored energy back into the environment and solidifying once more, ready for its next silent intervention. The applications extend far beyond a single chip. Within the walls of a Mars habitat, these materials can be integrated directly into the insulation. A blend tuned to melt at 22 degrees Celsius could line the living quarters during the heat of the Martian day, or if internal temperatures rise from too many occupants in a room, the material would liquefy, absorbing the excess warmth and keeping the interior comfortably cool. At night, when temperatures plummet, it would slowly solidify, releasing that stored heat and acting as a thermal buffer against the cold. This eliminates the need for massive, power-hungry heat pumps and air conditioning units, replacing their frantic activity with the calm, predictable rhythm of chemistry. The reliability of this system is absolute because its function is an intrinsic property of the material itself. There are no thermostats to miscalibrate, no coolant lines to spring a leak, and no pumps to seize up after a century of use. It is a form of thermal memory, a set-and-forget solution that operates on the timescale of atoms and molecules, ensuring that the environment within a spacecraft or habitat remains within a safe, comfortable band for generations, governed not by a complex digital control system, but by the timeless, unerring laws of physics. While the silent ballet of quantum locking and the steady push of electrostatic sails define our journey through space, the very heartbeat of any long-term settlement depends on a far more fundamental rhythm, the reliable ebb and flow of energy itself. In the stark environments of other worlds, this rhythm is brutally interrupted. A Martian colony, for instance, would face night cycles lasting over 12 hours and dust storms that can blot out the sun for months. On the Moon, the night stretches for 2 Earth weeks of profound, energy-starving darkness. Relying solely on immediate power generation is a recipe for catastrophe. Survival hinges instead on the ability to store immense amounts of energy during times of plenty and release it steadily during the long lean periods. This is the critical, unsung role of our 26th machine, static energy storage. Unlike the chemical batteries we use in our phones and cars, which degrade with every charge cycle and have lifespans measured in years, these systems are engineered for the century, designed to be charged and discharged tens of thousands of times with almost no loss of capacity. Two technologies stand out for their motionless brilliance and incredible longevity. The first is the advanced flywheel. Imagine a heavy, precision-balanced rotor, a massive disc suspended in a vacuum chamber not by physical bearings but by the invisible force of passive magnetic levitation. Once set spinning by surplus solar energy, this rotor becomes a bank of pure kinetic energy. In the frictionless silence of its magnetic cradle, with no air resistance and no physical contact to cause wear, that spinning motion can be maintained for astonishingly long periods. When power is needed, the process is simply reversed. The spinning mass acts as a generator, its kinetic energy converted back into electricity as it slowly decelerates. It's a concept as simple as a child's top, but perfected with material science and quantum physics to become a bedrock of planetary power grids. The second, even more motionless technology is the solid-state supercapacitor. While batteries store energy through complex chemical reactions that slowly break down their internal structure, supercapacitors work through the pure physics of electrostatics. They store energy by simply gathering charges on two surfaces separated by an insulator, with no chemical transformation involved. The next generation of these devices uses solid-state electrolytes and nanostructured materials like graphene, which provide a colossal surface area in a tiny volume for holding an immense electrical charge. This eliminates the liquid electrolytes that can evaporate or freeze and removes any possibility of the dreaded thermal runaway that plagues lithium-ion batteries. The result is a storage device that can be charged in minutes, discharged millions of times without degradation, and operate reliably across the extreme temperature swings of an alien world. Their potential to create truly resilient communities is profound. Vast arrays of these supercapacitors, charged by the relentless sun during the day, could power an entire Martian base through the cold night, their silent, instantaneous discharge capable of handling the surge in demand when all systems and lights switch on at once. Meanwhile, massive flywheels buried beneath the regolith for stability could store energy from entire fields of solar panels, spinning endlessly as a strategic reserve for month-long global dust storms, ensuring that life support, communication, and critical research never miss a beat. They are the ultimate insurance policy, the silent guardians of the night shift. By providing a perfect buffer between intermittent energy generation and constant energy demand, this technology transforms a precarious outpost entirely dependent on the weather into a self-reliant, robust community capable of thriving independently for generations. Its power security guaranteed not by complex machinery, but by the patient, unwavering spin of a wheel and the silent gathering a charge. But even with the most advanced energy storage and gravity simulation, a civilization spread across the solar system would face a silent, invisible threat: the loss of connection. The vast distances between worlds impose a cruel tyranny of delay, where a simple question sent to Mars can take anywhere from 4 to 24 minutes for a reply, making real-time conversation an utter impossibility. And for probes venturing to the outer planets, that delay stretches into hours, turning mission control into a place of immense patience and pre-planning. This challenge of staying in touch is compounded by the machinery we traditionally used to do it. The iconic parabolic dish, with its intricate gimbals, motors, and tracking systems, is a masterpiece of mechanical engineering, but also a collection of failure points slowly grinding themselves into dust under the relentless assault of time and the space environment. It is against this backdrop of isolation and mechanical fragility that the 27th machine offers its silent, steadfast solution: the passive communication array. This technology reimagines the very concept of an antenna, transforming it from a complex, moving instrument into a static, intelligent surface woven into the fabric of the spacecraft or habitat itself. The magic lies in two key innovations: metamaterials and fractal geometry. Metamaterials are artificially engineered substances designed with structures that manipulate electromagnetic waves in ways natural materials cannot. Think of them not as a solid block, but as a carefully arranged lattice of microscopic elements, each one shaped and tuned to interact with a specific frequency of radio wave. By patterning a surface with these metamaterials, engineers can create a panel that can bend, focus, or direct incoming and outgoing signals without a single physical movement. It's like giving a flat wall the signal-gathering power of a giant curved dish, but without the dish ever actually moving. The second approach uses the infinite complexity of fractal antennas. Fractals are geometric patterns that repeat themselves at every scale. The same branching shape you see in a tree's limbs is visible in its twigs and even in the veins of its leaves. This self-similarity is a secret weapon for communication. An antenna designed with a fractal pattern can be incredibly compact yet resonate efficiently across a wide range of frequencies, all while being printed directly onto a surface. A communication array built with this technology would have no moving parts to speak of. Instead of a single large dish that must constantly pivot and rotate to track Earth or another spacecraft, the entire hull of a vessel or the facing wall of a Martian habitat could be coated with a metamaterial skin or embedded with a fractal antenna network. This transforms the entire structure into a massive, omnidirectional ear and mouth for the cosmos. Signals from any direction can be received with clarity, and transmissions can be beamed out with precision, all managed not by grinding gears, but by software that electronically steers the signal by adjusting the phase of the waves across thousands of tiny elements on the surface. The advantages for longevity are transformative. There are no motors to burn out, no lubricants to dry up in the vacuum, and no delicate bearings to be pitted by micrometeoroids. The system is immune to the jamming and misalignment that could cripple a mechanical dish. Its durability is limited only by the enduring stability of the materials it's made from, which themselves can be chosen for their resistance to radiation and thermal cycling. This means a probe arriving at a distant world like Pluto could establish a communication link that remains crystal clear and perfectly aimed for centuries, its data flowing steadily back to Earth long after its original mission has been completed. For a colony, it means the lifeline to home is not a single, vulnerable piece of hardware, but an integral, unbreakable part of their city's infrastructure, ensuring that even the most remote outpost never has to feel truly alone in the silent vastness of space. But as we engineer our environments with silent machinery for power, propulsion, and protection, we must not forget the profound human need for an environment that feels less like a machine and more like a home. The harsh, artificial glare of LED panels and fluorescent tubes, while efficient, is a constant visual reminder of our separation from the natural world, a psychological weight that grows heavier with each passing year of a long mission. This is where the 28th machine offers not just a technical solution, but a philosophical one, blending the boundaries between the built environment and the living world. Bioluminescent lighting moves beyond the concept of a simple lamp, instead turning the very walls, ceilings, and gardens of a space habitat into a source of gentle, natural illumination. The principle draws from a dazzling display already perfected by evolution over millions of years, seen in the eerie glow of deep-sea jellyfish, the shimmer of fireflies on a summer night, or the ghostly light of foxfire fungi on a rotting log. These organisms produce light through a biochemical reaction, typically between a light-emitting molecule called luciferin and an enzyme, luciferase, a process that is incredibly efficient, producing almost no waste heat. The challenge for space applications is to harness this beautiful phenomenon in a controlled, reliable, and sustainable way. One approach is through genetic engineering. Scientists can take the genes responsible for bioluminescence in these creatures and splice them into other, hardier organisms that are more suitable for life in a closed environment. Imagine a strain of innocuous, non-toxic moss genetically tailored to emit a soft, greenish-white light. This living carpet could be grown along the baseboards of corridors, providing a gentle pathway lighting that guides crew members during the habitat's designated night cycle without the jarring intrusion of bright electric lights. Or consider a symbiotic relationship with the plants in an agricultural module. By engineering the leaves themselves to glow faintly, they could perform double duty, producing food and light simultaneously from the same energy input. For those wary of introducing entire living ecosystems into the delicate balance of a spacecraft, a second, even more passive approach exists: biochemical lighting. This involves isolating the luciferin and luciferase proteins and embedding them into an inert, solid-state matrix, a special kind of clear plastic or gel. This material can be formed into panels, tiles, or even decorative sculptures. When oxygen from the cabin air slowly diffuses into this material, it catalyzes the light-producing reaction, causing the object to glow with a constant, ethereal light. To turn it off, you simply restrict the airflow. To brighten it, you allow more. It's a light source governed by chemistry, not electronics. The benefits of this technology extend far beyond simple energy savings, though that is significant. This is light that feels alive. The quality of bioluminescent glow is inherently soft, diffuse, and easy on human eyes, lacking the harsh blue wavelengths of many LEDs that can disrupt circadian rhythms and sleep patterns. It would create a calming, serene atmosphere within the habitat, reducing stress and enhancing the overall sense of well-being for a crew that might not see true sunlight for years. Furthermore, it represents the ultimate in maintenance-free operation. A bioluminescent wall panel has no filaments to burn out, no complex circuits to fail, and no power conduits that could short-circuit. It simply exists, a permanent part of the structure, glowing quietly for years until the chemical reactants are eventually exhausted and need to be replenished, a process that could be as simple as applying a new gel coating. This innovation points toward a future where our technology doesn't just serve us, but lives alongside us in a more integrated, organic way. It transforms a utilitarian space into a living space, proving that the key to long-term survival isn't just about technological efficiency, but about creating an environment that nurtures the human spirit as well as the body. Yet even with the gentle glow of bioluminescent walls to soothe the mind and robust systems to sustain the body, the harsh reality of space ensures that illness and injury will eventually find their way aboard any long-duration mission. The human body, for all its resilience, remains vulnerable to a host of ailments, from the sudden trauma of an accident to the slow, insidious creep of cancer, a risk dramatically amplified by the constant background radiation of deep space. On a journey spanning multiple human lifetimes, the idea of a fully staffed hospital with MRI machines, linear accelerators for radiation therapy, and teams of surgical specialists is a fantasy. The machinery is too massive, too complex, too power-hungry, and far too dependent on a long supply chain of spare parts and consumables. This sobering medical reality is where the 29th machine reveals its profound necessity, offering a paradigm of healthcare built not on intervention, but on silent, steadfast prevention and treatment. Static radiation therapy units represent a radical rethinking of medical technology for an environment where traditional options are simply not an option. Instead of a multi-ton device that requires precise, computer-controlled motors to orbit a patient and deliver radiation from multiple angles, these passive systems are designed for simplicity and absolute reliability. One approach utilizes targeted radioactive isotopes sealed within precisely engineered capsules or plaques. Imagine a crew member diagnosed with a localized tumor, perhaps from a routine scan. Rather than a complex course of treatment requiring a machine that could break down, a medical officer could select a pre-made applicator, a small, curved shield containing a specific isotope like iodine-125 or palladium-103. This applicator, its radiation output and effective range perfectly characterized centuries earlier during its manufacture, would be placed directly against the skin or even implanted briefly at the tumor site. The isotope inside requires no power, no activation, and no monitoring. It simply emits its therapeutic radiation at a steady, predictable rate, delivering a precise dose to the cancerous cells while minimizing exposure to surrounding healthy tissue. After the prescribed time, the applicator is simply removed and safely stored. The entire process is mechanical, relying on the immutable half-life of the material itself rather than any fragile electronic control system. For deeper conditions or a broader approach, another method leverages focused fields. This could involve a system where a radioactive source is permanently housed at the center of a spherical chamber, surrounded by a collimator, a thick shield of lead or tungsten riddled with carefully calculated channels. A patient would sit in a fixed position relative to this source, and by manually rotating different collimator segments into place, the medical team can shape the beam of radiation without a single moving part in the source itself. It's a therapy device that operates on the same principle as a stencil, using static, physical barriers to sculpt the treatment. The implications for a generations-long voyage are immense. A small suite of these pre-calibrated applicators and collimators, each designed for a specific type of common malignancy, could constitute the entirety of a colony's radiation oncology department. Their operation requires minimal training, nothing like the years of specialization needed to run a modern radiotherapy machine, and their longevity is guaranteed by the natural decay properties of the elements they contain. They would never suffer a software crash, a power failure, or a mechanical malfunction. This technology ensures that a diagnosis of cancer on a distant world does not become an automatic death sentence, but a manageable condition, treated with tools as reliable and enduring as the starship itself. It demonstrates, perhaps more powerfully than any other machine, that the goal of motionless technology is not to make life in space more automated, but to make it more humanly possible, safeguarding our most fragile asset, our health, with the same silent, unwavering certainty that protects the ship from the void. And so we arrive at the final, foundational pillar of any self-sustaining civilization, whether on a new world or a generation ship sailing between them, the very ground beneath our feet. After mastering power, propulsion, and protection, our survival ultimately boils down to the ancient, irreplaceable art of growing food. But the soils of Mars, the Moon, or any asteroid are not like the rich, life-filled Earth of our home planet. They are barren, crushed rock called regolith, largely devoid of the organic matter and complex microbial ecosystems that make plants thrive. To till this hostile ground with the heavy, power-hungry machinery of Earth-based agriculture would be a losing battle against entropy, a constant drain on energy and human labor that could never be sustained for 1,000 years. The 30th and final machine in our journey offers a different path, one of profound patience and biological harmony. Passive soil enrichers are not tools we use on the land. They are a transformation of the land itself into a living, self-renewing partner in our survival. Imagine the process of preparing a field on Mars not with a roaring tractor, but with a quiet, deliberate act of seeding. Before the first crop is even planted, a rover would move across the designated area, dispensing not seeds, but a custom-engineered blend of materials into the top layer of regolith. This blend is the heart of the system. It contains slow-release mineral granules, perhaps rich in phosphorus, potassium, and calcium, essential elements that Martian soil lacks. These granules are coated in a biodegradable polymer designed to break down over decades, metering out these vital nutrients at a pace that matches the slow cycle of farming in a controlled environment. Mixed in with these minerals is a far more active ingredient, a powdered consortium of specially selected microbes. This isn't a single bacterium, but a curated community. Some strains are nitrogen fixers, capable of pulling the inert nitrogen that makes up most of the Martian atmosphere and converting it into a form of ammonia that plants can absorb. Others are mycorrhizal fungi, which form a symbiotic relationship with plant roots, effectively extending their reach far into the poor soil to scavenge for water and the minerals being released, delivering them directly to the plant in exchange for sugars. Once introduced, this microbial community becomes a permanent, self-sustaining resident of the agricultural plot. They establish themselves, multiply, and form a thriving underground network that operates entirely on its own, requiring no input other than the occasional addition of water and the organic waste from the very crops they help to grow. The agricultural module itself would be designed as a closed-loop ecosystem. Plant trimmings, inedible biomass, and even processed human waste would be composted and returned to the soil, not by a mechanical tiller, but simply by being spread on the surface. The waiting microbial workforce below would immediately set to work, breaking down this organic matter into rich humus, completing the nutrient cycle without any human intervention. This creates a soil that grows richer and more fertile with each passing season, a stark contrast to terrestrial farming which often depletes the land. The Enrichers do all the work of a modern fertilizer plant, an irrigation system, and a team of soil scientists, but they do it silently, continuously, and with zero energy consumption after the initial application. Their timescale is measured in centuries, their operation governed by the timeless rhythms of biology and chemistry. For a colony on Mars, this means that after the initial setup, the immense task of feeding thousands of people becomes a background process, managed by the silent, unseen billions of microorganisms working in the soil. It reduces the risk of catastrophic famine from a crop failure or a broken piece of farming equipment. The system is distributed, resilient, and self-healing. This final technology brings our journey full circle, connecting the highest aspirations of quantum physics and material science back to the most fundamental human need, to sow a seed in good earth and watch it grow. It perfectly encapsulates the overarching theme of these 30 motionless machines. Our future among the stars will not be won by louder engines or more complex computers, but by elegant, intelligent systems that work in harmony with the universe's own rules. It is a future built on patience, on the power of stillness, and on the profound understanding that sometimes the most advanced solution is to simply create the right conditions, step back, and let nature do the rest. Looking back across this incredible tapestry of 30 technologies, a powerful and unifying theme emerges, one that fundamentally redefines our relationship with the cosmos. For the entirety of the space age, our philosophy has been one of conquest, a belief that we must overcome the harshness of space with increasingly complex and powerful machines, forcing our will upon the void through sheer mechanical ingenuity. But this new paradigm, built upon the principles of motionless operation, suggests a different path entirely. It is a philosophy not of conquest, but of coexistence, not of forcing solutions, but of finding them already written into the fabric of the universe itself. These machines teach us to listen to the subtle rhythms of space, to the steady decay of atoms, the relentless push of solar wind, the silent exchange of heat, and the patient chemistry of materials, and to build systems that harmonize with these rhythms rather than fight against them. This shift from active struggle to passive synergy might be the most important breakthrough in our journey to the stars, because it is the only approach that scales across the unimaginable gulfs of both space and time. The true brilliance of these technologies lies not in any single device, but in the collective intelligence they represent, a convergence of physics, biology, and material science that points toward a future where our presence in space is not a fragile, high-maintenance endeavor, but a resilient and enduring state of being. Each machine, from the betavoltaic battery drawing power from atomic whispers to the quantum locking device floating supplies on fields of force, contributes to a grander vision, an ecosystem of technologies that support each other and their human inhabitants with minimal intervention. The waste from life support becomes the fuel for agriculture, the heat from electronics regenerates the air scrubbers, and the dust that pitted old spacecraft now powers their sensors. This is the essence of a closed-loop, sustainable civilization, one that has learned to use resources with such exquisite efficiency that it can thrive indefinitely, even in the most resource-scarce environments imaginable. It transforms the spacecraft or planetary base from a machine that must be constantly fed and repaired into a living, breathing, largely self-regulating entity, more akin to a natural biome than a piece of engineering. This vision of resilience is what makes the dream of interstellar travel and multi-generational colonies truly plausible. We are no longer just building machines to take us there. We are learning how to build worlds that can sustain us once we arrive. These motionless marvels are the quiet, steadfast guardians of that future, ensuring that the light of human civilization, once kindled, will not flicker and die in the cold, dark silence, but will burn steadily on, powered by the elegant, patient, and enduring intelligence of stillness. As we conclude our journey through these 30 motionless machines, it's clear that the future of space power lies not in louder explosions or more complex mechanics, but in silent, steadfast innovation, a philosophy where technologies work tirelessly for centuries without wear, without fuss, and almost entirely without our notice. This isn't merely an upgrade to our existing toolkit. It's a fundamental rethinking of what technology should be when the stakes are this high and the timelines this vast. These systems promise more than just sustainability. They offer a new ethos for engineering itself, one where elegance, simplicity, and profound reliability reign supreme over raw power and complexity. This shift in thinking might be the most crucial innovation of all, because it's the only approach that scales across the unimaginable gulfs of both space and time. Whether on the dusty plains of Mars, in the delicate equilibrium of orbital habitats, or on a generations-long voyage toward the stars, these passive machines will form the silent, unwavering bedrock of our cosmic legacy. They are the unsung heroes in the epic of human expansion, the technologies that won't make headlines for their roaring launches, but will instead earn our deepest gratitude for their centuries of quiet, flawless service. They ensure that our story doesn't end with a few flags and footprints, but continues for 1,000 years and beyond, written in the language of patient physics and intelligent design. Now we'd love to hear from you. Which of these motionless marvels captured your imagination the most? Was it the quantum locking devices that defy gravity, or the betavoltaic batteries that draw power from atomic decay? Share your thoughts in the comments below, and let's continue this conversation about the incredible future that awaits. If you enjoyed this deep dive into the technologies that will shape our next millennium, be sure to subscribe and hit the bell so you don't miss our next exploration into the future of tech. Until next time, keep looking